Okay. You said which one? 22? Yeah, how far does a gas particle diffuse in 1 hour if it travels 1 centimeter in 1 second? Okay. And so you need to see what the dependency is of diffusion, you know, on on time, right? And so there's a bunch of equations on that. Let me find those notes. That's how far it went. And so you need to find the equation of how far it goes. Um, so here's 22. You have two options here. You have this x versus r. And really the difference is it constrained or not? And so this is linear diffusion. So it's constrained to a single dimension, one dimension, like in a pipe. Whereas spherical 3D diffusion is unrestricted, and so notice it's three times. It's like instead of a two, it's a six. So instead of one dimension, you can sort of take it. It's a two for every dimension. Since you have three dimensions, you have a six in that denominator. But both of them are proportional to the square root of temperature. I'm sorry, time. I keep saying temperature. Both are proportional to the square root of time. And so once again, if you've got a proportionality here, then you could do the ones and twos. And there should be a 1/2 here. Okay. And so if it goes, it's 1 second, it goes 1 centimeter, that's R1 and T1, then there's 3,600 seconds in an hour. And so 3,600 divided by 1, and take the square root of 3,600, you get 60. So we'll go 60 centimeters. If it was directly proportional, it'd go 3,600 centimeters because we went from 1 second, 1 centimeter, 1 second. Where would it go in 3,600 seconds? Well, it would only go 60 centimeters because it's the square root of time. So that's 22. Was already in industry before I learned anything about viscosity, and the guy was up there and he's talking about, well, we assumed Fickian diffusion. And I was like, Fickian diffusion? I've never heard of Fickian diffusion, but it's Fick's law. But I was like, oh, that's what Fickian diffusion means. Yeah. Other homework questions? Yeah, Reagan said, hold on. Okay. On this one, let's see which one. 23 through 27. Okay, that's Poiseuille's law, at least 23, 24, and 25, what we did today. The flow rate, 1 atmosphere vessel, 10 atmospheres, so we're looking at changing the temperature. Remember that it's P2 minus P1, and so don't do P2 minus P1 equals 10 because it's the P1 is 1, so it's the difference. It's 9, not 10. It's the difference between those two, and people often make that mistake. They'll see P2 is 10, so they'll say that delta P is 10, but it's not. 10 minus 1 is only 9. So that's a place where people mess up. Here we do the viscosity is doubled, so 5 atmosphere gas line flows 1,000 liters per second into a 1 atmosphere vessel. What will be the flow if the viscosity is doubled? So we have a change in pressure and a change in viscosity. Okay, so actually no, this is there's no change in the pressure. That's the P2 and that's the P1. It's really unnecessary information. If we double the viscosity, we have the flow, and we see answer 500. So we're just We're not changing the pressure. That's just P2 and that's P1. Let me go find that equation for you. Okay, so we're going to pull this one up. See if I can paste it in. Do I have it pasted in? No. Okay, so we'll go back over here. Okay, now you can see the equation. And so what we're doing is this is, like I said, a 5 atmosphere, 5 ATM, 1 ATM. We're changing this one, doubling. And we got this flow rate here of 1,000 liters per second. So those are all the numbers in this problem. And the only thing that's changing is the viscosity. So look what I've done here. This is, if we put ones and twos on this, notice that the viscosity is in the denominator. And so up here you see F2 on top, eta 2 is on bottom because they're inversely proportional. Yeah, viscosity, that's the Greek character eta. Looks like an N with N with an extra long leg. And then F1 is on bottom, so eta 1 is on top. If you get those upside down, then you're going to screw this up. Okay. And so once again, we're saying that F2 is double eta 1 and eta 2. Eta 2 is double eta 1. So we would do this. So when we say it's doubled, we can just take this and put a 2 there. And what you end up with is a cancellation of eta 1. So you don't even need to know what it is. And then when we bring F1 over to the other side, we see that it's cut in half. So the flow rate of 1,000 liters per second is divided by 2, so we had 500. Yeah. And we didn't do anything with the 5 atmospheres and the 1 atmosphere because we didn't see in the problem that it was changed. So it was information we had. We could put it in the equation, but it didn't change, so it would cancel out. We just did this one, we said 1,000 liters per second. What would be the flow if the diameter was doubled? We noticed that, 2 R1 over R1 to the 4th power. The R1s cancel, and we end up with 2 to the 4th power, which is 16. So that F1 would be multiplied by 16 to give us F2. So this is the skill I want you guys to be really good at, is these proportionalities, because this is the one skill I used a lot whenever I was out working in the real world. They were constantly saying, what would happen if this happened? Or what would happen if the temperature in the room went up by 5 degrees? Or whatever, what would happen to all of these, the vapor pressure of this can or that, whatever. And I don't know what the enthalpy of formation or enthalpy of vaporization of this glue is, but I know the temperature dependence of the Clausius-Clapeyron equation. So I could say whatever vapor pressure it has, what would happen if the temperature went up from 298 to 302? Well, I could calculate that pretty easily, not even knowing the identity of this solution. I would say it'll only go up by X percent. So it's going to be minimal. Yeah. Okay. All right, we'll do some more questions on Wednesday, and then you guys will make 100 on the exam on Friday, and everybody's grades will go up, and everybody will be happy. I'll get great reviews.